The first forms of model selection we will look at are thresholding and pruning. And these are among the simplest forms of model selection that you can think of. The general idea is that we can think of some measures per edge, for example significance values, that tell us something about if this edge is substantial or not. And we can look at significance values, but also at, for example, Bayesian criteria or fault discovery rates or other things. So here I have 4 edges, 1, 2, 3, 4, that are significant below some alpha level. And I have 2 edges here, 1, 2, that are not significant. And the idea in both thresholding and pruning is then to simply remove those edges that are not significant. Very easy thing to do. So that's the idea. And in thresholding, we simply hide edges that are not there, hide edges that do not meet some criterion. So we can estimate a network and then simply hide these so that they're not visible, but we don't necessarily refit the model. So that means that in the model that we estimated, they're still there, these edges, you just don't see them in the network and we treat them as 0. In pruning, we actually remove the edges, so we fix them to 0, and then we re-estimate a model where those edges are fixed to 0. And that we can do. You can estimate a model, for example, using the G-Lasso package without regularization. I'll talk a bit more about it later. Or using the psychometrics package, you can fit a fixed structure of a network with other edge weights set to 0. So this is the same as thresholding, except that it takes one step further in also re-estimating the model, so that your parameter estimates are also based on the fact that other parameters are set to 0. And that's something you don't do in thresholding. So commonly you can do this based on, for example, significance values or bootstrap significance values. We'll talk more about bootstrapping in a later video as well. False discovery rates, base factor, credibility intervals, things like that. Now, if you did node-wise regressions, so if you estimated the network by estimating the incoming edges first per node, then you have 2 estimates of every parameter. For example, here we have one regression to predict A from B and one regression to predict B from A. It might be that they're not both significant. That can happen. So one might be significant, the other one might not be significant. Not generally in the case of the normal Gaussian graphical model, but in some more advanced cases it can happen, for example, multi-level estimation, that not both are significant. In the general case, they're actually equivalent to each other, so they would be both significant or not. But in case that's not the case, then you have to choose between including an edge if both are significant, which is the AND rule, or if one of them is significant, which is the OR rule. And that's really all there is to it in thresholding and pruning, that we look at per edge at some statistic and then based on if we include it or not, based on that statistic. So let's take a look. So this uses the estimate network function from bootnet with the default set pcore, which we already learned about in the previous video series as well. So this will estimate the maximum likelihood estimate of the Gaussian graphical model. And now we simply add these arguments threshold equals sig and alpha is 0.01 to remove all edges or threshold all edges that are not significant at an alpha level of 0.01. Here, instead of sig, we could also use some other things like Bonferroni, for example, or Holm, to adjust for multiple comparisons. So if you want to be really sure about every individual edge, you might want to do that. I generally don't recommend it because these are a lot of tests. So what you gain in confidence in your edges, you lose in the sensitivity in your power to pick up edges. So you get a very sparse picture, unless you have a big sample size. But that's something you can do. Now this is nice for some metrics like the pcore or for the pcore, we have analytic p-values, but that is not always the case. And also if your data are not normally distributed, for example, then it might also be that this is not the case that these p-values are actually correct. And for the Ising sampler package, which you can use for unregularized Ising model estimation, we also did not build in analytic p-values there yet. You could get them in principle, but they're not built in yet. So one other thing you can do is bootstrap the data and then remove edges that are not significant after bootstrapping. And bootstrapping we'll explain in much more detail in a later video, but it's a way to get basically a confidence interval around your edge weights, and then you can see if zero is in there or not, to do a test, a non-parametric test for significance of a parameter. So that we can do using the bootnet package that we'll also explain in a later video, and then with this boot threshold function. Now, very important to note, and this is actually something that we see done wrong quite often in the literature, is you don't want to combine this with other model selection methods. So in the next videos, I'll teach you about other methods like EBSU GLAS or GGM mod select, but they already do model selection for you. So then you don't want to do that and bootstrap and remove things because you're doing double model selection. You already did model selection, so you don't need to do that again. Alright, the BGGM package also has some very nice and powerful thresholding methods to threshold a network. So for example, you can use credibility intervals, which are Bayesian versions of confidence intervals. But Bayesian will argue that they are much better because they tell you something about the actual probability of a parameter being in that range. And you can, as the threshold networks that now remove edges where the zero is in the credibility interval by using the select function in BGGM. After you run the estimate function, that's different from the explore function that I showed earlier, because the estimate function is the only difference really is the prior use, and this one is more appropriate for credibility intervals. You can also threshold based on the base factor in BGGM, and that's the same code, but then you use explore instead of estimate. So explore has priors that are really suited for base factors rather than credibility intervals, but the idea is more or less the same. So that's how we do that. Then these are all thresholding methods. So far we have not actually refitted the model. This is something that I call pruning, which you can do in, for example, the psychometrics package. So here we remove edges based on some criterion, but then we also refit the model. So in psychometrics, the way that you do that is by using the GGM function to generate a model, or the async function to generate an async model, to run it, the same way we explained before. And then you use the prune function. And here also you can adjust for multiple comparison and things like that. A very powerful thing about pruning is that you can do this recursively as well. So it could be that now that I prune these edges, some other edges also not became significant anymore, and this can also be pruned afterwards. Another powerful thing about it is that we are actually doing model selection. So we can compare this model to a model with all edges included, because we actually refitted the model and we got fit measures for that as well. Okay, so that's thresholding and pruning. Now these methods are very fast. They have some very nice properties like fixed false positive rates. So if you set alpha is 0.05, then you have 5% chance of including false positives. So 5% of false positives will be included in your network. And you know that. With other methods, you don't know the false positive rate. It could be high, it could be low. It really depends on the network structure. You have non-biased estimates, which means you have maximum likelihood estimates or posterior mean estimates. They're not biased. That is more in comparison to regularization methods that I'll talk about later. But there are also some downsides. If you do thresholding, you don't actually do model selection. You're only hiding edges that might not be there. It can lack some statistical power. It can be very conservative, but you might not be able to pick up edges again if you don't follow up the pruning, for example, with a model search that we'll talk about later. And one particular problem I think is that the sample variation can be quite high, and also you're sort of guaranteed to include 5% of the false positives. You have a false positive rate of 5% if you set alpha to 0.05, or 1% if you set alpha to 0.01. Which means that you will include false positives. Well, every method will do that. But the false positives that you include will be very substantial because they all pass the threshold needed to reach statistical significance. So they might be a little bit more prominent in the network, especially as the lower sample sizes. And I think this is especially the case in the async model. So the async model, like the Gaussian graphical model, has parameters that goes from -1 to 1 because they're partial correlations. The async model has parameters that goes to -infinity to infinity because they're log linear regression slopes, not partial correlations. That means in the Ising model, some small fluctuations can lead to much stronger effects in the graphical representation in the network. So an edge that might be like 2, for example, might suddenly be 3 due to sampling variation, and a false edge might be very strongly prominent in the network. So especially for the Ising model, I like this a bit less than the regularization method that we'll talk about later, mainly also because of this. A final problem with thresholding and pruning that's not always possible because often we don't know the sampling distribution of these edges, and then we can bootstrap, but that might also be very computationally challenging sometimes. Okay, that's it for the video on thresholding and pruning.